In regular business applications, searching is one of the most common tasks. This entails retrieving data from data structures such as arrays, lists, and maps, etc. This search activity, more often than not, decides the application's responsiveness to the end user. Searching algorithms are used to look for and retrieve elements from any data structure. Based on the type of search operation, these algorithms are generally classified into two categories: linear search and binary search. This course helps to understand the different ways of searching data with less complexity and optimized form, where we will talk about searching algorithms. Learners will learn to code the two searching algorithms, linear search as well as binary search, using Java programming. So without any further ado, let's get started right away.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you don't miss out any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. As it said, knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I will definitely respond to your comments. Hello everyone. Welcome to the session where we'll be talking about searching algorithms and its implementation in Java programming. So before going ahead with the session, let me tell you the agenda for the session. So what all we are going to discuss today in the session is algorithmic analysis of any given code. Like what is algorithm? What is the different types of analysis we do for any given code or any given algorithm? And then how to find out the space and time complexity for a given code, may it be in any programming language. Then we'll go ahead and talk about the different searching algorithms, that is linear search and binary search. So the concept behind linear search will be discussed, and then its implementation in Java programming will be talked about. Then we'll go ahead and talk about the time and space complexity of linear search. Similarly, for binary search also, we'll talk about the basic idea and a concept behind binary search. Then how is binary search implemented? And then we'll talk about the time and space complexity of binary search algorithm as well.
Let's try to understand what is an algorithm. It is a step-by-step approach to solve a particular problem. If there is a problem, what is the things that you are going to take care of? So the solution that you give should be crisp, right? It should be exactly what is required, right? If a problem is about swapping two numbers, you should be able to swap two numbers and with the most efficient approach. And when you define an algorithm or when you are writing an algorithm, it should be understood by a non-technical person, right? There should be no such language dependency in your algorithm, right? So this is what an algorithm is: a step-by-step approach to solve a particular problem. Your problem can be complex or it can be an easy problem. It is free from programming language. There are multiple possible algorithms to solve a given problem. Let's suppose I told you to swap two numbers, right? Now, one algorithm is wherein you can go ahead and create one temporary variable and then swap them. The another approach is that you're going to use addition and subtraction operators to solve the same. You're going to use these operators and you can solve this problem of swapping two numbers, right? Which one do you think is the efficient approach? Obviously, here you're using an extra variable and here you're not using any extra variable. So this seems to be a better approach. And obviously, it should be understood by a non-technical person. You should not be using language dependency code, like you should not use any language agnostic code, right? So it should be language independent. So let's see what is an algorithm analysis. This is again a step-by-step approach to solve a particular problem. It helps us identify which algorithm is optimal. Okay, this is the analysis part of algorithm, right? Herein, let's suppose I told you to swap. It helps us to understand the trade-off between time and space complexity, right? So there should be always, you should be able to understand the difference between time complexity and space complexity. And depending on that, you should be able to do a trade-off as well. Now, when I mean trade-off, you should be able to depict that are you going to keep your time complexity efficient, or are you going to use your time efficiently, or are you going to save your space. So let's suppose you are given an example, right? Let me give you an example. So you are given an example, you are given an array, and in that array you want to search an element. Now the first approach is that you will go and search one by one, right? You will go here, you will iterate through here and here and here. You try to search an element, right? Let's suppose you are searching for 4. In the worst case, you are traversing a big O of n time, right? And in the best case, you are traversing big O of 1 time. This is the best case and this is the worst case, right? So these are the two cases. But this code in itself, whenever you are traversing in a linear fashion, is inefficient, right? And if you're trying to search for an element using different approach, let's suppose you are using a binary search and then you are trying to search an element, obviously your time complexity will reduce. The best case will again remain big O of 1, but it will reduce to big O of log n. Now there are certain parameters, or depending on these parameters you can define the best, worst and average case of a given problem. So now there are different types of algorithmic analysis, that those are best case, average case and worst case. Okay, so the best case is obviously when you are searching for an element in an array of, let's suppose, 100 size, right, or 1000 size. The best case is that the first element that you look, if you're talking about what, linear search, okay, best case scenario is that the element that you're trying to search is the first element, right? Done. This is your best case and it requires constant amount of time. Now if you talk about average case, it will be somewhere around the middle, right? About 1000 divided by 2, or you can say big O of n divided by 2. Since we are neglecting, we do not take care of these constant terms, or we can negotiate or we can neglect these constant terms, because as soon as our input is increased, right, let's suppose right now we are talking about million, thousand elements, we are talking about 10 billion elements. At that time dividing it by 2 still is same, okay, not same, but it can be ignored, because as soon as we are increasing our n, let's suppose, to 10 crore or more than 10 billion, okay, 10 100 billion is the input size, right? At that time dividing by 2, still it is greater than what we can do if we have something around log n, okay. So obviously the average case is still big O of n. Now when you talk about worst case, the element is found at the end, or it is not even found in the array. You're traversing each and every element in the array and still you were not able to find the element. So this is the worst case, okay. Now the worst case is always taken into consideration because this is the maximum resource that you require, okay. When you talk about time complexity or space complexity, right, so time and space, right, so you always talk about worst case scenario, right? And you always deduce your time and space complexities based on worst case. It is computed because the analysis as it dictates the maximum resource requirements. So worst case helps us to find what are the maximum resources that this is going to take, okay. So we keep track of those things and we allocate resources in such manner. So we always talk about worst case. Now let me give you an example of linear and binary search. So in linear search, right, we always talk about it, and in binary search the space complexity of both these algorithms is constant in worst case, right? And if you talk about the best cases of linear and binary search, it is again constant, right? And it is again same, okay. Now when you talk about, we go off on, now when you talk about the worst case scenario, right, and this is what helps us to differentiate between binary and linear search. The worst case scenario, the worst case scenario for linear search is big O of n, wherein for binary search it is big O of log n. Now let's suppose there are 8 inputs, you're going to traverse 8 times in it, in this linear search. But if you have this log 8 to the base 2 value, it reduces, or you can reduce it to 3 into log 2 to the base 2, which is 3 times. So in this, you are only iterating 3 times. In this, you are iterating 8 times. Now, as you can see, that input is very low or very less. That means there are only 8 elements. As soon as what our input, our n, or the number of elements in the array grows, this size of these iterations become substantial, and that is for the same reason we always talk about worst case scenario. Okay, now let's talk about time complexity. It determines the total number of unit operations to be undertaken to solve a particular problem. Right? Let's suppose, let me take an example of number of iterations. Like, so if you are able to search an element in a single unit of operation, then it is termed to be a constant operation. And if you're doing the same for number of inputs, that let's suppose there are n elements, and you're traversing to find a particular element, you are traversing n times, so it's termed to be a big O of n. So to solve a particular problem, you determine the number of unit operations. Now, unit operation is an operation that is independent and it can be broken down into simpler operations. It is independent of architecture. It is computed on the basis of algorithm itself. You have an algorithm in place, and based on that, you compute the time complexity of each and every step. Right? If there is a loop, what will happen? If there is a if condition, what will happen? If there's a while loop, what will happen? It's high priority critical in optimal algorithm selection. Now, depending on this time complexity, you can determine whether you want to go with a particular algorithm or not. Because let's suppose you're trying to search an algorithm, right? You can have two options, right? You can use a binary search or you can use a linear search. Now, depending upon the time complexity, binary search works much more faster as compared to linear search. It works in order n and it works in big O of n. So time complexity plays a major role, and there is always a trade-off between the time and space. And in this session, we will be covering both of these things. Okay. So now let's take an example and let's try to determine the time complexity of that particular example. Now let's suppose you are given a for loop, and in that for loop, you are iterating from 0 to n, right? Where n is I is less than n, and then you're doing the plus plus. Now you're doing some work in it, okay? Now since you're traversing from 0 to n, now this is a scenario wherein this will be operated or this will work. The number of unit operations that are present in this for loop is big O of n. Now similarly, there is another for loop in the same program which is operating from 0 to n, okay? And then the same thing, there's a nested for loop in it, and therein what you are doing, you are traversing from 0 to what, let's suppose this is traversed, n is 8, right? N is equal to 8, and in this for loop you are traversing 8 times, and in this while loop you are traversing 3 times, right? Let's suppose you are multiplying every time by 2, okay? So now in this for loop, the nested for loop, the time complexity of the same is n log n. Now, why it is n log n? Because if you observe carefully, number of operations that I told you is 8. So outer loop is working 8 times and the inner loop is working log 2 to the base 8, that is 3 times. So now what is the scenario? What will be the total time complexity? It will be big O of n plus big O of n log n. Okay, this will be the time complexity. Now, now what is happening over here? This is a scenario wherein what is happening? It is happening m into n. That means you are multiplying big O of n, that is the nest for the nested one, okay, into big O of log n. So you are multiplying it. Whenever you have a situation wherein you have a for loop inside a for loop, therein you will multiply the time complexities. Now you have a for loop outside, and then you have this nested for loop. For this nested for loop, you have n into log n, right? And for this, you have what, big O of n. Now this is a scenario wherein what happens, m plus n, and in this you will always take into the consideration the maximum number of resources that are there. so that one for loop will take. So in this, you're taking only n resources, or this is the time complexity of this is n, and in this you're taking n log n. So obviously this is greater, right? So you always say that the time complexity of that particular problem will be n log n, because you're neglecting these smaller terms. As soon as our input is increased, these terms will be neglected and they will not be that much significant while you're allocating resources. Now, what about the space complexity? It determines the total space to be allocated in order to solve a particular problem. Now, whenever you are using any extra space in the algorithm while you are implementing it, that is termed to be as space complexity. It can be in the form of arrays, that extra array that you have used to solve a problem, or an extra linked list that you have used to solve a problem, or a stack or a queue, right? It involves memory of the computer, right? You're involving memory, right? You're taking something extra, right, to solve a particular problem. Let's talk about merge sort. Therein you take extra memory, and in worst case you can take big of n extra memory. That means the number of elements that are present in the array, you're taking the same array as an auxiliary memory, that extra memory, right? It's low priority critical in optimal algorithm selection. When you talk about space complexity, we try to avoid any extra space. We try to solve it with minimal space, right? So that we don't use any of these auxiliary memories. Okay. Now let me take an example of a merge sort, wherein in that merge sort, every time you create a left array for the left side and the right side, every time you create these subarrays and then you calculate and then you divide them into further and further unless there is no possible division, and then you start merging them. So again, this is a condition, or this is a scenario wherein you are using extra memory of big of n. Now if you talk about simpler examples, let's suppose you are trying to uh, change the positions of even and odd numbers, right? So let's suppose you have these indexes, right, in the array, and you have some values. Let's suppose 10, 20, 15, 20, 15, and 10. Let's suppose these are the values, right? Now you want to use, or you want to find out the frequency of these numbers. So you will be using another array, and in that array what you will be doing, let's suppose you are picking up this 10 and you are storing it in this. Now you'll be checking, okay, if this is already present, pick up the counter and keep track of how many times this 10 occurred. Now this will work only for when you're trying to search 10 throughout the array. I'm taking a naive example, right? So I'm taking this example and I'm trying to search 10 and I'm trying to calculate how many times it has occurred. So you place a 10 in this array, and then what you're doing, you will just iterate through the array and then keep a track of this, how many times this has occurred, and keep incrementing your counter, right? So now you're using an extra space, right? Now even if this example is not understood, let me take another example. Let's suppose you're using a recursion, right? Now you might be thinking, okay, internally you are not using any extra space, but what happens in recursion? Every time a recursion is there, that means function calling itself, an activation record is created and a stack is used internally, wherein your main function will be there and the number of function calls, right? The function calling itself, function calling itself, function calling itself will be we will be pushing it on the stack, and once you have returned, then we will be popping it out, right? So internally you are using an extra memory, and it depends on from program to program. Are you using big O of n, or are you using log n space? But internally, recursion uses extra memory. So an auxiliary memory, or you can say that extra memory, is used while you are using recursion. So that is why we try to avoid recursive problems, and we try to solve our problems using iteration. So, which is obviously that we are not using any auxiliary memory, although it is internally, but still recursion uses extra memory, and that thing is taken into consideration. Now, you might be thinking, okay, now should we use, or should we save space, or should we use less time? Should we go for time efficient algorithm or space efficient algorithm? Now, there is always a trade off between space and time. So, in some problems, they might ask you to save or to write an efficient algorithm keeping the time into consideration, that you don't have to use extra time. But in some, they might say, okay, you can use extra space, but time should be efficient. Or in some cases, they say you use as much time as you want, but space should be less. So that is also there. So there's always a trade-off between both of these things.
Now let's see how we can find the time and space complexity of any given code or algorithm. So basically here I am going to give you some tips and tricks when it comes to finding the time complexity of any given code, or for that matter even space complexity for any given code. So what happens in any programming language? There are certain constructs or certain programming concepts which we use. Like for example, conditional loops, conditional statements, then no looping constructs. So nested loops. So how does time complexity is found or in these cases? And also the space complexity, like what is the total space being taken while executing that particular code. No space, when I talk about how many variable at a time resides in memory, that decides the space complexity. Okay, and time complexity is again the total time taken, maybe in terms of n we calculate. If suppose n is a number of input, so if n or 2 is a number of input, so for 2 input, what's the total time taken for each code to run or to execute? So we'll assume there are n inputs, and for n given input, how many times the particular code runs, that decides your time complexity. Okay, so I'm going to talk about few small tips and tricks about finding space and time complexity to you, starting from the first aspect, that is your looping constructs. Okay, so if I talk about loop, the very frequently used loop is your for loop. So let's see if int I is equal to 0 and it goes till I less than n and I plus plus, and then there is some statement here, maybe x is equal to y plus z. Let assume that all these variables were declared before in any programming language for that matter. Okay, so what will, if I tell you that okay, find out the time complexity, what time this complete code is going to take if n is the input. Okay, what you will do is, okay, if I assume there is no the number of input is only one, so the for loop will run only one time, and this complete statement will run only one time. So time taken is only 1 unit of time, right? And what will be the space taken that time? Only this variable, these two variables will be stored at a time in the memory, right? So no matter what is the input, every time you need only two variables at a time to be stored there in memory. And when the sum is done, that is discarded, and then only there is only one variable then after that, right? So space complexity is constant here, right? Only 1 unit of space is taken, because every time, no matter how much is the input, every time that same two variables occupies the space. So space here complexity will be O of 1, but time complexity will be, for one element this for loop will run only one time, so time complexity will be also 1 unit of time it is going to take. For two no elements, this for loop will run two times. Similarly, for n elements, this for loop is going to run n times. So this statement will be executed how many times? N times. So we can say that it takes O of n unit of time. Okay, big O of n unit of time it takes to run the code. Okay, now coming to the another thing is your nested loops. Okay, so guys, whenever you find the smaller codes, you can fragment together and find out the overall time complexity for any larger code. So talking about nested loop. So nested loop, how it runs, for is int, suppose I is equal to 0, I less than n, I plus plus, and then inside this there is one more for loop. Okay, maybe int j of 0 to j less than n, j plus plus, and then this there is a statement, maybe same statement I'm writing, int x is equal to y plus z, and then this closes the bracket. Now how many times this code will run? Again, space complexity is going to be O of 1, guys, because you can see the actual operation being done is only this, and every time it requires 2 unit of space. So it's constant throughout the execution. It doesn't depend on the number of inputs. So it is O of 1, the constant time, the constant space. Talking about time complexity. So you see here, for each value of I, j runs from 0 to n. So if value of I is 1, Or you can say value of I is 0, then this runs from 0 to n, that is n times. If value of I is 1, then also this runs from 0 to n times. If value of I is 2, then also this runs from 0 to n for n times. Similarly, so on. Okay. It means if this goes from 0 to n, this will also go from, for each value of I, it is going to go from 0 to n, 1 to n, because it's less than, not less than, equal to. Or you can say 0 to n minus 1, right? It means what? For I value as 0, this code runs n times. Then I value of 1, this code runs n times. I value of n, this code will run n into n times. Yes or no? Like, are you getting my point? So this is mathematical concept here. So n into n, that is the time complexity for this will be O of n square. Right? Now, coming to the third type of a concept, if-else loop, conditional statement. Okay. So if says if, and there is some statement over here. Okay. Then it says else, and then some statement over here. Suppose the time complexity of this is O of n, and time complexity of this is O of n square. Which will be the final time complexity out of this complete if-else loop? Final time complexity will be whichever part of either if or else, whichever part has less time complexity, which is taking less time to execute. If this is taking n times to execute, this is taking n square times to execute, definitely n is smaller, n is lesser value than n square. So the overall time complexity for out of this if else loop will be O of n. Is it clear? Right. Okay. So this is your these are the three constructs. Now let's see if there are sequential statements. Like definitely in any given program, there's not only just for loop or just a nested for loop or if else loop. There are other statements also along with these loops. So in that case, how the time complexity or space complexity is taken care. Again, guys, here I'm not told about space complexity in this if else loop. So space complexity again depends on what statement is being over here. Like at a given point of time, how much is the space being occupied in memory to execute that statement. Does that space allotment depends on the number of input? Then how it depends on number of input will be your space complexity. Otherwise, it always remains constant. Fine. Let's see the fourth aspects where there are other statements also along with these looping constructs and conditional statements in a given program or a code. So now the fourth condition which I'm going to see here is that suppose there is a statement, x is equal to y plus z. Okay. Then there is a for loop over here. Then there is maybe do while loop. So it does something and then while loop is there. Okay. Then there is again maybe some statement, some statement here, maybe a is equal to a plus plus. Fine. Now let's see so what you'll do is you'll start from the beginning of the code. So first code here takes how much time? Is it dependent on the input? No, every time it's going to be y plus z only. No matter input is 1, 2, 3 or whatever. So it is constant time. Suppose this for loop, whatever is the for loop over here, this takes time complexity of O of n. Okay. Then there is this do while loop, which also takes a time complexity of O of n. Okay. Then there is this a is equal to a plus plus statement, which takes constant time. Okay. Then in this case, what will be the final time complexity? So the final time complexity is going to be the summation of all, that is 1 plus n plus n plus 1. Okay. And this will be your, so constants are always removed because it doesn't play much role, because constant is going to be always taking constant time. So that doesn't affect our performance, right, of the code. So we'll remove those. N and n. So n plus n will be 2 of n, right? Again, this is a constant which will be eliminated, and this will be just n, right? So the total time complexity will be O of n. Suppose out of this, one of the time complexity would have been O of n square. Correct. So the time complexity here, suppose this is, so in that case it will be 0, 1 plus n square plus 1. Correct. So O constants will be again removed. It will be n square plus n. Right. Again you see here, no, compared to n square, n is a smaller value. right? So our main focus should be on the bigger values because this becomes negligible in front of this one. So our total time complexity will be O of n square only. Getting it? So that's how the time and space complexity is calculated for any given code. Basically, time complexity, some tips and tricks I gave you here, which you can use to calculate. No, simply by just looking at the code, you can make out what is the no time complexity for that given code. There are other methods also like Master's theorem, which is properly used for finding the time and space complexity, but that's a time-taking procedure. It's for a full, process or steps which you have to follow. But these tips and tricks will help you quickly find out or verify the time and space complexity of your given code.
Now let's talk about searching algorithms. And the first searching algorithm that we are going to talk about is linear search algorithm. So what is linear search? It helps us to search an element in a linear data structure. Now let's talk about one example wherein we will be searching some element inside the array. So let's suppose this is an array and the elements are 10, 20, 30, 40 and 50. Now if we are trying to search an element that is 50 inside this array, how linear search works is that it checks each and every element that is to be searched, right? That is there in the element array, right? Let's talk about this example here, 50. Now 50 will be compared, right? We'll check, is this 10 equal to 50? No. Is this 20 equal to 50? No. Is this 50 equal to 30? Is this equal to 40? Is this equal to 50? Yes. So here we were able to do a linear search, right? We were searching for this element inside this array one by one. We compared first with 10, then 20, then 30, and then 40, and finally then with 50. At the end, we were able to find this element in the array in a linear fashion. Now, this is what is termed as linear search. Now let's talk about linear search algorithm. Since it is a very straightforward, or you can say a brute force algorithm, right? It's a brute force algorithm of finding the element in the array. So this is how it works, right? We have one for loop wherein we will be what iterating through all the elements, that is from 0 to n, and inside that what are we doing? We are looking for the item, that is that element that we want to search, right? Let's suppose this is 50, right? This 50 will be, we were checking if this 50 is equal to the element that is ARR of I, right? And then if that is the case, if we find out the element in the entire array, we will return its index, right? That is index, right? That I we will return this I. Now there might be the case as well if we are at the end of the array and we have exhausted the last element as well and we were not able to find this 50, right? Let's suppose this is 10, 20, 30 and 40. Now this 50 is not present in the entire array. At that time, what we are going to return is -1. So we will say that, okay, we were not able to find this element whenever we are returning this -1 in this array. And this -1 indicates that we were not able to find that element.
Now let's see the implementation of linear search algorithm. I'll go directly to the Eclipse IDE and will start writing the code. So here I have created the class search, and then there is a public static void main method. Now inside this we'll be writing the concept or the logic for search. So as you saw already, what is the logic behind the linear search, and that is that you have to linearly search each and every element in a given array one by one, starting from the 0th index. Okay, here I'm using array. You can use any other data structure also to perform linear search on it. But linear search concept is always that you have to start from the beginning and one by one keep on searching till the end. Fine. So let's see its implementation. So for that, first I'll create a array, okay, which we are going to search. New int, and I'll define the array itself over here. Maybe 6, 4, 5, 8, 2, 1, 9. Okay. So this is the array defined. Now let's perform linear search on this. So we'll take the user input, that which element the user wants to search, or which the integer value among the given the user is looking for or searching for. So for that, to take the input, we use scanner class in Java. So scanner s1 is equals to new scanner, and in the bracket we pass as a parameter the input stream. So system.in represents that I'm going to provide input through keyboard. For this I have to, I think, import the class. Yeah, so scanner class has to be imported. Now we'll take the user input. So let's put a comment also here. Enter the element to be searched. Okay. Now we'll take the user input. So int maybe key is equal to s1 dot. So you can see here next int is a method which is used. So we'll use it directly here. Done. Now comes the main logic of the search, linear search. Okay. In that we'll run a for loop that will begin from the beginning of an array and will go till the end of the array. And at every index we have to compare that the value at that index, is it equal to the key that is being searched. If it is equal, then that index should be returned as an output. If it's not, then it should say that the number doesn't exist which you are looking for. Okay. So that's the whole logic. Let's write a code for it. So as I said, we'll be using for loop for int I equals to 0. I should be less than what? A1 dot length. So A1 dot length gives the total length of the array, whatever is its length. So in this case, it will give you 1, 2, 3, 4, 5, 6, 7. 7 as an output. And then I plus plus. This for loop, what you have to do? Compare. So again, for comparison, you have to use if loop A1 at ith index, is it that equal to the key which we are searching? If it's equal, then what should be done? If it's equal, then we should print first of all element is at index I, right? That's it. Okay, what will happen if the element doesn't exist in the complete array? What has to be done for that? Okay, here there should be this. Okay, as it is a string, it should be in double quotes. So yeah, so what should be the case when there is no element, that element being searched is not there in the array? So in that case, let's use a logic here. What I'll do is I'll initialize one variable that is maybe count is equal to initially 0, and every time when it is, if it founds any number, it will increment itself. Okay, so count will be 1 now. And if suppose it doesn't find that particular element in the complete array and the complete for loop runs, so count will remain 0, because it will only increment if this if loop is true, and if loop will be true only if condition will be true. So if condition will be true only if any given element in the array is equal to the key which you are looking for, right? Until unless count will remain 0. So that's what the logic I'm going to use. So after this, I'll write that if count is equal to 0, then in that case should print that element not found in the given array. Fine. That's it. So that is the simple logic behind your linear search. Now let's see. When we run this program, it asks the element to be searched. So these are the elements 6458219. So out of this, suppose I give as the 8 as an input. Okay. So it says, okay, one second. Element not found in the given array is also being printed, and the output is also being printed. So let's see, something is a mistake. I think this closing of the loops. Yeah. This should be outside the for loop. Okay. The for loop ends here. So outside this, it should be Now let's run, check if it gives the correct output. So yeah, you can see 8 is the element entered. So it says element is at index 3, 0, 1, 2, 3. So yeah, at the third index, 8 is present there. Right? If I enter some, look at, like I'll run the program again. If I enter some value, suppose 78. 78 is not there in the array. It should say element not found in the given array. So that's the simple logic behind your linear search. So we saw the implementation of linear search in Java programming.
Now let's talk about the time complexity of linear search. Now, if you observe carefully, let's try to understand this best case, right? So now if you are looking for the element, and let's suppose these are the elements in the array. Now, let's suppose in best case, what can happen? You're looking for 10 and 10 is the first element in the array. Now, how many iteration did you require? Did it require to find you the 10? None, right? The constant time, right? Only one single unit operation was done and you were able to find this 10. So this is the best case time complexity where the element that you're trying to find is the first element that you search, right? In this case, you are looking for 10 and 10 is the first element. So this is your best case. Now, what about the average case and the worst case? Now, let's suppose average case is that you were looking for an element which is at the middle point, right? Let me just see. 0, 1, 2, 3, 4. Now, or you can put another and looking for 60. Now, in this case, or you can just skip it, okay? No need to add one more. Okay, so now you're looking for an element which is somewhere around in the middle. Okay, in this case you're looking for 30. Okay, so now if you observe, you are only iterating half of the elements, that is 5 by 2, which is nothing by n by 2, since constants doesn't play in do not play any role when you're talking about time complexity. So that is why average case still boils down to big O of n. Now, what happens in worst case? You're looking for an element that is 50 and which is present at the end of the array. Or in the worst case, you're looking for something that is not present in the array. That is 60, let's suppose. And in that case, you will still iterate through the entire array. And that is why the worst case time complexity in that case will be big O of n, because you are iterating through the entire array and that element was not found. You're looking for 60 and that is not present there. So you're iterating through the entire array, that is n operations are done. So that is why it boils down to big O of n. Now let's talk about the space complexity of linear search. When we are trying to find the element in the array, that is 10, 20, 30 and 40 and 50, we were not using any extra memory, right? We were not using any auxiliary memory, that is what we mean by auxiliary memory or extra memory, in order to find that element. We were just looping around these elements one by one, and we were doing it on this particular, on the same array that we were given, right? Since we are not using any auxiliary memory, that can be in the form of what? A stack, a linked list, or an array, or a string, or a queue. We are not using these auxiliary memories because they are not required, right? We are searching for an element in this particular array that was given to us, right? So the space complexity of linear search is constant, right? We were able to find it in a constant amount of space. Okay, we are not using any extra space. Now let's try to understand binary search algorithm. What is binary search? So binary search is one of the searching techniques, right? Like we saw in linear search, wherein the time complexity of linear search was big O of n, right? We were iterating through all the elements, and now this is a much more efficient algorithm as compared to linear search. Now again, why do we need searching is the thing that, let's suppose if you have a given set of elements and you want to search if that element is present in your array or not, that time, right, we can use either linear search or binary search. Now binary search is much more efficient and it is used on a sorted array, or it can be used on an array wherein some order is maintained. because based on that order, we will divide our array, right? It is a searching algorithm which is or which follows the divide and conquer strategy, right? Let's suppose this is our array, and now since it will be divided in such a way that we can neglect one part of it, right? We will be dividing and then conquering. That means we will be then searching for our element. Now, let's suppose we are looking for something that is, now let's take an example wherein this array is written or the elements contained in this array are in such a way that we if we skip this part, or the left hand side will be skipped or the right hand sides can be skipped in such a way that they don't affect our output. So every time in linear search, our search space is reduced unless and until we find that element or the array is exhausted. Okay, so our search space is reduced to half in every iteration. So this is what a binary search is. We'll look for an element in such a way that every time we are neglecting half portion of the array. And let's take an example when we have this entire array. So first half, that means if four elements, eight, if there are eight elements, four on this side, four on this side, these four will be neglected. Then we have two on this side, two on this side, these two will be neglected. Then one on this side, one on this side, then this one will be neglected until unless and until we find that element or the entire array is exhausted, right? So this is how your binary search works. Now let's try to understand binary search algorithm. So first we are going to understand the iterative approach, and then we are going to understand the recursive approach. So iterative, as the name suggests, we are going to use for loops, right? We will start with a for loop and it will iterate, and we will iterate unless and until the beginning is less than the end, right? So because we will be updating our both beginning in some cases, and in some cases we'll update our end. Now, what happens? Now, since we know that in this iterative approach or in this binary search, it doesn't depend whether we are using iterative approach or recursive approach, the logic will remain same, right? So we will be having this array and it will be in some order so that we can neglect some part of it. It doesn't have to be sorted always. We can still apply binary search even if the array is not sorted, but still some order is there so that we can neglect some part of it, because again, keeping this thing in mind that it follows the paradigm of divide and conquer. So now we have this beginning and end at place, and we will always iterate when beginning is less than end, right? So now what happens after that? Now we have this array, and now what we will do, let me take new pointers. So this is your beginning and this is your end. So this is your beginning and this is your end. Now you will be taking a new middle index, right? M, let's call it M. And now let's name these things 0, 1, 2, 3, 4. So you will do what? Beginning plus end divided by 2, so that some part of it can be neglected, right? So it will be 2. So your mid is at this position. Now you will see, okay, the element that I'm looking for is, let's suppose, is 50, and the element that I am currently at is 30. So obviously it will be never from this side. There is no chance that we will be able to find 50 from this side, that is the left hand side, right? First we will check, okay, is this 30 equal to 50? No. So this will never be executed, right? Then we will check, is my item that is there, is this 30 less than or greater than 50? If it is greater than 50, right? If the element that is, if item that is 50 is greater than 30, right? Which is in this case, our 50, that is the element that we are looking for, the item is this point, is greater than 30. So there is no point that it will be on this side. So we will skip or we will neglect this half portion of the array. So that is why our new beginning is updated. It will be new, it will be middle index plus 1, that is middle index was 2 plus 1, that is this will be our new beginning. So we have smartly skipped the half portion of the array. So now let's rub all of these things, and now let's see what happens in the next iteration. Now we'll keep this thing in mind that we are not looping or we are not exceeding this limit, that is beginning should be always less than, or it should be always less than or equal to end. Okay, so this condition should be maintained. And similarly we'll again divide our array and then look for the same things, right? First we'll look for the element, then we'll skip some part of it. So this is the iterative approach for binary search, right? Now let's look at the recursive approach or recursive algorithm for the same. So again, beginning, the ground rule will remain same. We'll always iterate or we will always recursively call binary search unless and until this beginning is less than end. Done. Now what happens, we'll again find middle index, that is beginning plus end divided by 2. Then we will look for the element. These three steps will remain same even if you're using recursive approaches. Now what happens in recursion, right? We again call the function again and again. That is what is recursion. So in this entire tutorial we will be covering recursion as well, but in the later part of the course. Here you can get a good intuition, or let me give you a brief intuition about how recursion works. So let's suppose this is your activation record. Every time when a recursion is there, an activation record is called. So let's suppose you have these three statements. And let's suppose in your algorithm you have statement P1, P2 and P3, right? And at P2 you are calling the function again, right? You're calling this function again. So now what happens, an activation record is called. He will check, okay, is this statement executed? Yes, so one will be executed. Is second executed? Yes, so second is executed. But at second you're calling this function again, so at that time again a new activation record is created. Now this third step is left behind, right? Now this will be covered when we come back or return from this function call that we called here. So let's suppose this function was here. Now in here you are returning, right? This function called, let's suppose this is not less than beginning, beginning is not less than end. So this will be somewhat, this case is relatable, right? This is similar to what we are looking for, right? Let's suppose there is some similar situation wherein beginning is not less than end. At that time you will be returning from this. Right now once you have returned, you will be then calling this function again, but this time around for this. And let's suppose this time around you are calling this, one is executed, step one is executed. Now again this activation record is called, this activation record is one, and then again this is called, right? This is executed again, this two is called again, a new activation record will be created, and these three steps, the step third will be still left for execution. So now here you return, right? Then it will go back to this step, right? And then once you are done with this, now there are two positions or two possible scenarios where you can return. Either you are returning from this function just like we have executed this condition and we return, right? Another is that once you are done with this entire activation record, at that time you will also return. Okay, so these are two scenarios. Now you have executed this, there is no step to be executed, it will return. Now this was left behind, this will be executed. Now nothing is to be executed, it will go to the caller, which was this, and finally it will go to the main method wherein we call this at the first place, this function. Okay, so this is how an activation record is created, a stack is maintained. Okay, even if you might be thinking we are not using any extra space, but whenever recursion is there, an extra space that is in the form of stack, that stack is maintained. So you need to keep this thing in mind while you are playing around with space complexity at the time when you're using recursion. Okay, so now with that being said, let's clear our screen and let's see how recursion is called here. So again, now recursively what we will doing, if now we have this mid, right? And let's take an example of an array 0, 1, 2, 3 and 4, 10, 20, 30, 40 and 50. So middle index will be 0 plus 4 divided by 2, that is 2. So this is our middle index, right? So this is 0, this is our beginning and this is our end, right? So now we are hit here, right? So we again check the 50 that we are looking. This is our item that we are looking for. Okay. So is 50, and this is our middle index. Is 30 greater than 50? No, it is not in this case. So this will never be executed. This is not executed as well, right? Now, what about this condition, the else part? Now, what we will be doing, we'll be skipping, since this 30 is less than, we'll be skipping this part and we will focus on middle index plus 1, which is nothing but this. So this will be our new beginning and our process will start moving, right? So now again, then the same thing will happen unless and until this condition is false, okay? So this is how your binary search works when you're using recursion. So now let's try to understand binary search and let's see its demonstration. Okay. So we are looking for 20 and this is our array, right? 10, 11, 16, 20 and 23. Now this array is sorted, right? So we can apply binary search. Okay. Since we can neglect some part of the array based on some conditions. Okay. So now our beginning in the first iteration, what is happening? Our beginning is 0, our end is 4, and our middle is this element. Now what we will be looking for is 16 equal to 20. No, it is not. But 16 is less than 20. So we will skip this part. In the next iteration, what happens? We'll be focusing on these three elements, right? That is 20, we will be focusing on this part rather, if we say. We'll focus on this part, right? Focus on this part. Okay. So now in the second iteration, what will be happening? Our beginning is updated. Now our new beginning is this point. Our end will remain at its own position. Now we'll find the middle index. So it will be 4 plus 3, that is 3, that is 7, right? And divided by 2, it is 3.5, right? So since this will be truncated, right, the truncation will happen and the integer that is there, the middle index will be 3. So this is our middle index, right? So you can see middle index is 3. Now, is this an element that we're looking for? Yes. So we'll return the index. So we found our element at index 3 and hence we return 3. Because if you observe carefully, it is returning, if the element is found, it is returning the index. So this will be returned, okay? So this is how binary search works.
Now let's see the implementation of binary search algorithm in Java programming. So I'll directly go to the Eclipse IDE and we'll type the code there. So yeah, I'm already here on Eclipse IDE and I've created a file which is having a class named as search, and then public static void main method is also created. Now let's create a function for binary search and we'll call that function of binary search from the main method on a given array. So to create a method, public static void, not void, it's going to return the index which is found wherever the element is found. So binary search is nothing but it's a searching algorithm, right? And we have to search for a given key in any given array. And if it is found, it returns the index. If it doesn't found, then it says that the element is not found. So it will return int, that is the integer, the value of an index where the particular value is found in the array. So int, let the name be binary search. And it takes what all it takes as a parameter. So it takes the array as a parameter. Okay. 1 second. Yeah, it will be A1. So first it takes an array integer in which you have to search for the given number. And then it takes the value which will be searched by us, right? So it may be an int value as it is an integer array. So let's have that the user is searching for an integer number. So let it be a key. And then to implement binary search algorithm, we need the first starting index and the last, that is the ending index of a given array. So that has to be given as a parameter here in this function of binary search. So int first and int last. Okay. Okay, so it's giving an error saying that you have to add a return method. So need not worry, as when we'll add return method, that error will definitely not be highlighted over here. Now, what's the logic of binary search? So binary search does what? As the name itself says, binary, meaning half. It divides into two halves. From the mid of the given array, it divides the array into two halves. Okay. The first, from starting from first index to the mid is one array, and from mid to the last is another array. And then it searches in the respective half. Like for example, the element which you're searching for is greater than the element in the mid, then it will search the second half. If the number you're searching for is smaller than the middle element, then it searches the lower half. That's the logic behind binary search. Let's write that. So what will happen that, okay, if will come later, first we'll write int mid, we'll find the middle element. Then only we can divide into two halves, right? So middle element will be first plus last divided by 2. Right? Let's put this in brackets. Okay. Middle element found. Now let's divide it. So for that we have to put a condition first. First condition is that always the search should be between the given range of an array. That is between first and last. Correct? You should not go on like searching, like suppose the arrays are stored from index 0 to 10. And there's no point searching after the index 10, right? Or before like 0, that -1, -2. Correct? So which the first condition is that is first should be less than equal to last. Okay. Now inside this condition, all other conditions will come. Now that what is that condition? If suppose the given key is found at the mid of the value, like it is dividing from mid, like the numbers, if the number is lesser than the mid value, then it will search the lower half, greater then it will search the upper half. But what if it is equal to the mid value itself? That also has to be checked. So if key is equal to mid, then in that case it will just return that particular index, that is mid. Okay, it will be a closing here. Okay, now if it is not at the mid, then what has to be done? Then if, okay, if the key is less than the mid value, then in that case what has to be done is go to the, or implement the binary search again on the lower half of the complete array. So you have to return from here what? Binary search, that is you have to call the method again. It's a recursive call to the same function, and here you will pass the array itself a1, and then you will pass the key. Now what will be the first element? First will remain first, but end will become the one value lesser than the mid -1, right? Then it comes as else. You have to return what? Binary search and implement on the given array a1. Input will be the key. In this case, your last will remain the same, but your first will change one value more than mid because the second half is being searched now. So mid plus 1 will be your first and last will remain your last. Getting it? Semicolon. Okay, we'll see what's the error here. Unreachable code. Okay. Let's fix this. So mid is here. Okay, this is opening here, closing over here. This is closing, correct. This is closing over here. Correct. Okay, let's close this over here. Okay, so okay, so it is closing over here. Now, what if the element is not found at all? It gets searched everywhere and still it's not found. Then in that case, it should return -1. Fine. Now let's go to the main method and call this function. So for that, first we'll create an array itself. A1 equal to new int I'll define the values also over here. Let's take some random values: 4, 6, 2, 9, 1, 7. Okay. And let's call the binary search as a function, right? So let's call this. It will store the value in the index, binary search, and I'll call over A1. The key I'm searching for, I'm giving it manually here. Suppose I'm looking for 6. The first will be your 0. First index is 0 in the array, and the last index is array length -1, because length starts counting from 1. So 1, 2, 3, 4, 5, 6 will be the value, but actually the index starts from 0. So it will be 1 less than 6, right? 0, 1, 2, 3, 4, 5. So it will be A1 dot length -1. Okay. Then we can put a statement here saying that if your index value is equal to -1, then in that case, it should print that element not found in the given array. Okay. Else it should say element found at index plus index. Okay. Let's run the code. So I'm searching for 6. 6 is there in the array, right? So it would say the, okay, cancel it. There's some error is what it's showing. Okay. So there will be a semicolon. Right. Let's run the code. So it says the element not found in the given array. So I'm looking for 6, but it's not being found. So it's returning -1. Okay, what's the error? Let's try to fix it up. This is A1 dot 0. This is A1 dot length -1. 2. Okay, we'll see here. Some issue with this, I guess. Yeah, so I looked at the error, and what I could see here is that if we change the numbers here, that is the elements of the array, to be in ascending order or in sorted order basically, because the first requirement of implementing binary search is that the element given should be in a sorted order. Okay, because then only you can compare that from the middle element. If the key is greater, then it should be in the later half, that is second half. And from the center element, if the key being searched is smaller in value, then it should be in first half. And that comparison is only possible if it is in a sorted order. So that's the only change I did here, is that change the values of the array, that is the elements in the array. And then let's try to execute it with, suppose I'm searching for 3. Okay, here I'm hard coding it with the key which was being searched. This is 3 over here. So let's run this code and check. So you can see here it says that the element 3 is found at index 1, starting from 0. So 0, 1. You can check for any other. So maybe 6. Also, if we check, so we'll get that it is at index 3. So 0, 1, 2, 3. So that's how the binary search works. If suppose I'm checking for something which is not there, then it should say that the element not found in the given array. Okay, so that's all about your binary search and the implementation of binary search in Java programming.
Now let's talk about the time complexity of binary search. Now, in the best case, now what is the best case? Now let's take an array, and in that array, 1, 2, 3, 4, and 5. These are the elements. Now, the best case is that not that if the element, like we saw in linear search, this element, when we are looking to search for this same element, at that time that was the best case scenario for linear search, right? But in this binary search, the best case scenario is when your middle index is at this location, and you're searching 3 in the entire array. So at that time, this will take a constant amount of time, and this is the best case time complexity in that case. Okay, now in average case, what happens, right? If you talk about this algorithm, let me just clear out my screen. So it follows a paradigm of divide and conquer. So let's suppose you have 8 elements first in the array. It will be divided into 4 because these 4, or either it can be on the left side or on the right side, will be neglected. And then we deal about these, then we focus on these things, okay? These 4 elements. Again, it will be divided into 2 and 2. Then we will neglect 2 elements. Then 1 and 1. Then again, there will be one of the element can be neglected. So there are 1 and 1. So we focus on this element. So the entire operation will be done, or entire searching will be done in 3 steps, right? Now, if I take an example, and if I do a log 8 to the base 2, what should be the value of this? Obviously, when I do this can be written as 2 raised power 3, right? And this can be written as 3 into log 2 to the base 2. Now this is 1, and now you get the answer as 3. So this 3 and this 3 are equal. That means if I talk about the worst case time complexity of binary search, it will be somewhere around log n. As we saw in 3 steps, we were able to find the element, and the log n, that means log 8, is the answer of that is also 3. So you get the point, right? So the worst case time complexity of binary search is log n, and same goes for the average case, wherein it will be somewhere around log n divided by 2, neglecting log n divided by 2, neglecting the constant terms. It will be again, or it boils down to big O of log n. Okay. Now let's talk about space complexity of binary search. Now, when you talk about space complexity, right, we only think of auxiliary memories, or you can say that what any extra memory that you guys have used. Since we did not use any extra memory, that can be in the form of array, or it can be in the form of stack, or it can be in the form of queue, or linked list, or even strings, right? Since we never use these extra memories in our implementation, so the space complexity of binary search is big O of 1. That is, it takes a constant amount of space.
Let's summarize the session. So in this session, we discussed about what is algorithms, what are the different algorithmic complexity analysis we can do over any given algorithm or a code. Then we talked about how can we find the time complexity for a given code, either it's a for loop or a do while loop or nested statements or simple statements or a codes written in any programming language. We can find the time and space complexity of those was discussed. And then we saw what is the idea or a concept behind linear search, and then went ahead and implemented the linear search algorithm in Java programming. And then we also did the complexity analysis. What is the time and space complexity taken for linear search? And then we discussed the concept behind binary search. And also we went ahead and implemented binary search in Java programming. And then the complexity analysis of binary search was also done. That is, we found out what is the time and space complexity for binary search, how much space and how much time relatively depending upon the number of inputs is taken by linear search, and binary search was also discussed in the session. I hope you liked the session. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you don't miss out any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. As it said, knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I will definitely respond to your comments.